let's go. So today we're going to be doing the heat transfer analysis here and relating how the methods and the differential equations that represent heat transfer get used to obtain the stiffness matrices and obtain the nodal values for heat transfer problems. So let's see, let's look at the objectives, and for now I'm going to disappear. And here, what are the objective here? Let's look at the heat transfer by conduction and convection. So what's the objective here? We want to find the temperature distribution, obviously, on a device, a part, or just any model that we create in 2 or 3 dimensions. We want also to find the thermal stress distribution of things. So in this particular case, we have the governing differential equations that we have in this case. Let's see. You have this equation here. So let me just get, okay. In general, the governing differential equation for heat transfer condition is like this. This is the heat transfer condition for when you have three dimensions, basically. So what you have is a situation where you have this kxx. This is the properties of the material, and d squared td x squared and dy squared and dz squared plus q. So before we had this situation that we had this heat transfer here with only one of these and none of these. Now in 3D we have all 3 dimensions for the partial differential equation that we need. So in here, you know, T is the temperature, and the K, X, X, K, Y, Y, and K, Z, Z are the thermal conductivities. Now, why are we writing it with those two, you know, with X and Y and Z, though? Because we could potentially have a composite material that has properties differently in different directions, right? So Q is the heat generated by the body, and then this is the value Q. Also, in temperature problems, we need to consider the boundary conditions. The boundary conditions. If you have a heat transfer problem, like you have one for, let's say, convection, then obviously that needs to be considered differently too. Yeah. So the general equation that we have for the boundary conditions is similar to the one that we have for the heat transfer here. So either you lose heat by convection, which is the fluid around a device. Let's say like when you blow on something, that heat transfer is, or cooling is, by convection. Like the cooling on your car, you know, the part of it, because not everything is just by the air flowing around, but also due to heat flux is um, the other situation. So what we have is in this case that the temperature on the boundary is unknown, and T infinity is the fluid temperature, and Lx, Xy, Ly, and Lz are the direction cosines, so that we account for the heat flux at a particular direction. Okay, let's talk a one-dimensional problem. How does this work? This is a one-dimensional problem, let's say similar to if we were to do, let's see if we can make a little drawing here, so that I can explain you this. Let's see, one-dimensional problem where you could just draw something like a fin, for example. In here you have, let's say this is a fin in here that we're going to draw. And you specify, let's say, t equals to, let's say, 100 degrees. No, let's say 10 degrees here, but t over here is 100 degrees. T0 or 1, let's say, is equal to 100 degrees. So when you have this fin, you divide it into finite elements. You divide it into sections like this, and what you'll have is that the heat distribution of this, you will have something like this. For example, the distribution of the heat of this would, could go like this curve, like that. So for a one-dimensional problem, we have this equation. See, we don't have the other 2D here. So this is the Governor differential equation. And then you have the, this is the equation for the boundary conditions. Okay. So in here you have the author has defined for you how you are going to calculate the heat conductivity matrix. We cannot call it stiffness because it is on it's not the elasticity problem, but it's the equivalent of a stiffness. In fact, that's what it is. It's the equivalent of stiffness. And that's where you see the calculations where we say element conduction, or say stiffness matrix or so. Using the methods of chapter 7, the author takes advantage of the fact that you can use matrices and the properties of them, of the elements, to establish this individual matrix. And of course, there's also, you have to add the, say, stress distribution, and then the one for heat, for convection. So there's the temperature distribution. This is nothing new. The temperature solution is the matrix of the shape functions times the nodal values, right? And so you have this this conductivity matrix, which would be the one of the properties, and then you have this G, which starts in three-dimensional, obtain the gradient. And then you have, in this case, you have this vector in here that accounts for convection as well as for conduction and heat transfer. So in here there are other simplifications from the ones that here the author made on chapter 7 to obtain these products of the shape function transpose and so on. So here's an example of how you do this. Let's say for this element that we're analyzing here, you have that this is the conductivity times A divided by L, and then this one, and then some other contribution, and then finally the other end. So normally this would have three terms, for the conduction and convection. The same way as we stated before, using the derivation of chapter 7, we obtain the vector of known quantities considering all the heat transfer, convection, conduction. Okay. Let's just do one example. Here you have this fan here. This is what I was trying to tell you. You have this. Do you see here has been divided into 5 elements and 6 nodes. And so that's how we do the objective in this case. Find the element equations, the equations for a one-dimensional finite element that can be applied. Okay. The first 4 elements are of course identical, because we have this. Let me see if I can use this. Yeah, good. Okay, so here you have the first 4 elements. They are almost identical, except this one that has this one has the convection, right? So the equations for this one-dimensional element, you have it in here. This is the equation for the individual stiffness matrix, and then follow the other terms. Okay, so it boils down to defining one stiffness matrix of an element to be able to globalize global stiffness. So with this in mind, we put some numbers. To the coefficients in here, and you have them right there for H and HA and so on. Now, once you have in this in here, you need to put it into the sum like that. And then do the same thing for F. F is this is the load vector, right? So you have to consider that there's no heat transfer on the first, and then develop the other ones accordingly. Okay, this is a good way to figure out these quantities in here. Once you do one, the global stiffness matrix for one is not that different from the others finite elements. So this is the vector of known quantities, of known quantities. And basically those H coefficients are the coefficients in the in the different parts of the model. So if you use the global stiffness matrix as outlined over here, you have this kind of equation. You see, this is interesting because in here you have this area of the matrix that has numbers, but the other two they don't have. So in here you apply for the stiffness matrix, and you will have to superimpose some elements, because let me show you. If I can actually draw this, it would drive the point home, and that is if you have this matrix in here, what you have is this as an individual matrix, and then the other ones are you see it overlaps here too. You see what I mean? This is what so you have in common this. Okay. So then you can see how we get the global stiffness matrix. Once you solve these equations, then you will be able to do this you will solve for these nodal values, and at that point you have solved the heat transfer problem. Okay. Now here we have another example in here. This is the affine gain, and it has a cross-sectional area like this. Okay. So you considering here a couple of other things that not on the past example. Here, for example, the element capacitance that we, as we would like to call it here. See, this is interesting. Using the directed stiffness procedure, you establish for one, and then establish for the other one, and then for the other, and so on. This is how we make how big this becomes, because you have this and this together. Okay. The objective of this whole thing, as you know, is to obtain a global stiffness matrix in this way, because having it this way is really helpful, because all these are zero. So the more zeros we have, the better. And then we have another example here. And in here you have, of course, the shape functions for a one-dimensional element, as you see. The necessary matrix for the element equations can be evaluated. So this is more towards the mechanism in which you go about finding these matrices for heat transfer problems. They are all based on the nodes, on the nodal. They're based on the coordinate of the nodes and whatever you okay, you have this n sub I and n sub j, and then we have the direction cosines here, and we call the material property matrix. Now, these are things that you need to have on a sheet of paper. You know what each one of these equations do, because it would be difficult to remember. But if you follow the definition of the vectors, it's pretty straightforward. You come up with an answer on this, on the other side right here. Okay. Number 2. I already told you that the author of your book had another reason to have you solve this when we were just setting out the problems. He wanted, well, maybe not solution, but how you set it up. Although once you get on the solution, you realize many applications have the same equations and be resolved similarly. This is to evaluate each one of the integrals there. And finally come up with this blue, the ones that is in blue contain the global stiffness matrix, and this for convection and this for conduction. Okay, so let's try again, but now with different boundary conditions. As you can see, there has been a list of updates here. Convection, paint, okay, so in here we have a, if the conduction coefficient is the surface all around, which is what this is in here. Now, in this case, we have the global stiffness matrix based on the integration methods. And this is what you'll end up with. Okay, so we have is let's go take a look at the two-dimensional field. Of course, this is always a challenge, but I want to remind you and bring you back to page 57 of your textbook, and you will find these definitions on the right-hand side that you see here. Okay, in here, remember the shape functions, how they were? That's n sub j and n sub k and n sub I in there. And we define all these matrices in chapter 7, right? No, chapter 5, I believe. And then you have a matrix. Matrices are mainly made for the coefficients. And you have a basic conduction matrix composed as you see here. And then we begin looking at the expressions that the author had derived, some in terms of C, some in terms of B. Now you have K. K now it composes of all these matrices. Okay. Remember the area coordinates? How do they work? The area coordinates are something that you have on the bottom and conduction on the other two surfaces. Okay. See, this is why the author of your book was trying to get you to practice products of shape functions, shape them square, all that stuff. Is because he has the motivation to help you. Okay, depending on what else it's on it, what other conditions you have, they need to come in here. Okay. The bottom line is we have developed three matrices for each side. Now, when you have an example like this, for example, you have a heat transfer problem that has a heat loss on two surfaces. You go back and use the same equation for the differential equations. Okay, so in here we're gonna see what we're gonna do with this section. They're not parallel, they're congruent. And so in here you have use the equations here. Okay, So you can see the idea is to be able to put in that global stiffness matrix all these other effects that we named them here. See? Some of okay. So here we go. This all, you know, it took me a while, but this is on page 57 of your textbook. What did I just do? Ooh. Here's where we were. And then global, using matrices, you can use all kinds of mathematical tricks to get the answer quickly. And so you have this global stiffness matrix that has been calculated like that. Um, and then this equivalent force matrix, which is the uh, on this using the local area coordinates. Now you could have a situation where you have a two-dimensional finite element and it has either a well or it has a sink. Mm. So this we want to generate of heat that occurs in a small area of the volume. The hard and then you have the impulse laws there. Okay, when you have a point source or a point sink, you have to account for this. And this is what this is showing you how to do it. Okay, here's an example where you have a triangular node, triangular element. Now we have everything. Okay. And then follow the equations that we learned in chapter 7 on those matrices. The idea is to come up with individual stiffness, the individual stiffness matrix, and go on from there. So you can take a look at this in detail on this web page.